interested in similar things and doing similar things. I then went to Holland in 74, 73, I guess, during the energy crisis. It was very nice because Holland was closed on Sundays, which was great. Could walk around in the streets. Stayed there for half a year and came back, and Jan came to the United States for about a year at about that time. And that was right after completing his dissertation in 73 on canonical analysis of categorical data, which is what he's still working on, basically. We actively worked together for about 5 years and published a series of papers together. And since then, he has continued working on those things very actively, resulting in a Gifi book and other publications related to that material. And I've been working on similar things, only somewhat less actively. I've been more involved in graphical things lately than that. But the graphics are specifically to try to communicate the results of doing these kinds of analyses. So I'm still very interested in these topics. Jan is chairman of the data theory department at the University of Leiden in Holland, and it may be the only department of data theory in the world. Is that true? It's probably true. It's a very nice setup. And he's been there ever since before 72, since he got his degree there as well. And I'll go ahead and turn it over to you.
Thank you. Well, I want to start by saying that I'm also very pleased to be here. I hope it will be a nice seminar. As Forrest has already explained, the order in which we shall discuss things is a bit different from the order in which was announced on this beautiful announcement. The main reason is that I will pay a little bit more attention to general principles and general ideas, and a little bit less attention to specifics. Of course, if somebody's really interested in specifics, then he can also always talk with me about them. For instance, during the second week, I'll be here another week after this seminar is over. It's after next Friday. And I'm perfectly willing to discuss any specifics that I have not talked about in the main course, or I mean any other questions that you may want my opinion about in the second week. I understand that there are people from various disciplines here with various backgrounds, and with what's always the most important thing to know is perhaps, except for the examples people will be interested in, also the level of mathematics that people have. I will not require a great deal of sophistication in mathematics. There are places in the Gifi book where there's more mathematics, but these are the places which are called specifics now. I will not go into them into any detail unless you have questions about them. What I shall try to do first is to put on the overhead projector, yes. Is to place our approach to multivariate analysis in a somewhat broader and more general framework. I'm not, oh, this is certainly not readable. Starting problems. it's also perhaps better to put out. Yeah, it's, the only possibility is completely out or. Wow. Okay. First, I want to talk about some aspects about the distinction, if it's a distinction, but about the relationships between what is often called data analysis and what is often called statistics. The understanding being that our work is in what is usually known as data analysis, and other person's work is in what is usually known as statistics. It is interesting, both for me and for those other persons, I would say, to look into the fact in how far that is true and in what sense that is true. First, we'll look at two definitions or two discussions of the term data analysis, which are the most familiar. The first one is perhaps most familiar over here. It's the discussion by Tukey in his famous 1962 paper in the Annals of Mathematical Statistics. And Tukey was, I think, in the English-speaking world, the first one who made an effort to replace statistics, the discipline of statistics, by the discipline which he calls data analysis, and which is supposed to be much more general than statistics. According to Tukey, data analysis has three important aspects. It has inferential aspects. Inferential is meant in the sense of reasoning from sample to population, and it is what the statisticians are usually concerned with. Data analysis has, still according to Tukey, incisive aspects, and these aspects are what later became known as exploratory aspects. This means that you look at data from various sides, you apply one particular technique, you look at the results of that technique, certain things become apparent, you apply another technique to sort of focus in on these aspects. This is exploratory and incisive in Tukey's terminology, and data analysis also has allocative, design aspects. And Tukey says there is more. According to Tukey in this very same paper, article, there are various stages in which the analysis of a problem, the quantitative analysis of a problem, progresses. The stages are listed briefly in black on the transparency over here. You probably cannot read my handwriting very well, but I will read them out so that will be a problem. All these things that I'm saying here are more extensively in the book by Gifi, so if you want to read it up later, that would be the place to look it up. You can also read Tukey's original paper, of course, that's even better. The stages are, the first one is recognition of the problem, formulation of the problem. The second stage is to use one technique, one quantitative technique, to analyze the data. The third stage over here, I have various fancy pointing things. The third stage is to use competing techniques. Overkill. Competing techniques apply different techniques to the same set of data and compare the results. Then a more advanced stage, and Tukey really talks in terms of more advanced stages, would be rough comparisons of the techniques in terms of efficacy. Sometimes it's difficult for me to pronounce an English word in the right way, but I think efficiency. Comparisons in terms of precise criterion is an even more advanced stage, but Tukey always says a precise criterion is necessarily inadequate. Optimization in terms of precise criterion will be the next stage, and the last stage is comparison of the results in terms of various criteria. Now, what is commonly known as mathematical statistics is often identified with A5, stage A5, optimization in terms of a precise criterion. And Tukey's paper and Tukey's definition of data analysis is that that is a much too narrow definition of what people normally do with data. And the rest of his paper is sort of devoted to showing that many more things can be done with data than optimization of a precise and therefore necessarily inadequate criterion. This is not exactly a definition of data analysis, it merely shows some of the components that such a discipline would have. Another contribution is the one by Ben-Zachary, which is probably less familiar over here. It's very familiar in France. As a matter of fact, it's very close to being the law in France. Ben-Zachary's definition of data analysis is summarized very nicely in a paper he has written for a conference in Honolulu. Unfortunately, the paper is also in French. So I have translated some of his principles of data analysis. There's a more extensive translation again in Gifi. And the 5 principles of French data analysis are, very briefly, statistics is not probability. The model must follow the data. Use as many variables as possible. We need computers. But the mathematics is classical. And of course, Ben-Zachary refers to Laplace. The first principle is most interesting, I would say, for our purposes. Statistics is not probability. Ben-Zachary explicitly means by that the techniques of data analysis are more heavily dependent on linear algebra, on matrices, although French mathematicians don't like matrices, but on linear algebra in a general sense than on probability theory. And in this respect, Ben-Zachary agrees with many other data analysts, I would say. Another recent data analyst of some fame is Kalman, perhaps known to some of you because of his famous work on the Kalman filter. He has also written a number of papers in which he defends very similar principles for data analysis, and in which he also implies or states that the main discipline that you need to look for if you are a data analyst is not probability theory, but linear algebra. Now, of course, the other principles are a bit, well, we need computers, use as many variables as possible. I will not go into them in detail, but it indicates what kind of data sets Ben-Zachary is thinking of. He's thinking in terms of large, relatively unstructured data sets with many, many variables which you cannot analyze by hand or by methods, for instance, by looking at small sections of the data, because they're simply too large. It's also important to memorize that the mathematics is classical and dates back to at least to Laplace. Ben-Zachary says that this is not very important, the computer is much more important. He said that the fact that the mathematical principles were available to Laplace did not make it possible for Napoleon to conquer the moon. Basically because Napoleon didn't have a computer, which is a rocket in this context, of course. There's a third field of data analysis which I also would like to mention here, and this is hardly in Gifi. The book by Gifi is from 1981, and many things happened in the world since 1981 and could not have been taken up in Gifi for obvious reasons. So one of the things that happened was that computer-intensive statistics is becoming rapidly more popular, and there are a lot of papers published in the statistical journals, which could be described as being about computer-intensive statistics. There's also robust statistics here, which is a somewhat more classical discipline, although also not that classical. The principles of robust and computer-intensive statistics are also, again, phrased very briefly over here. Replace models by supermodels. Now this means that instead of working with a sort of narrow defined probabilistic models of classical statistics, the normal distribution for instance, you work with much more general models, of which these narrow models are special cases. So you do not necessarily believe that your narrow model is the true model describing reality, but you merely assume that there's a family of models in which one of those models is the correct one, the true one. The second tendency is to replace assumptions by computations. This is sort of a strong statement, but people active in that field actually make this statement and see no reason not to repeat it here. There are papers by Diaconis and Friedman, and in which it's actually stated that instead of making the strong assumptions of classical statistics, you can now avoid these strong assumptions and replace them by massive computations. And this is the same as a shift from parametric models, strong parametric models, to much weaker non-parametric models, which now have become feasible because of the computer again. The third maxim of computer-intensive statistics is create your own stochastic environment. That sounds very up-to-date. It means basically that instead of assuming that your data are a random sample from some sort of probability distribution, you construct your data in such a way that that is automatically true. And with this, I refer to the techniques which are listed in green down here, the jackknife, the bootstrap, and subsampling techniques. We will meet them again in many of our examples, so I'll have opportunity then to explain what they are exactly. I'll kill myself with this. But basically these techniques are based on not assuming a particular probability model that has generated the data, or not necessarily assuming such a model, but introducing the probability model by random sampling, by using a random number generator yourself. So again, you do not need to make assumptions, you replace your assumptions by computations. Another example of that particular tendency is the use of randomization and permutation tests, which is also rapidly becoming more popular, basically because computers are becoming faster. And there's of course robust statistics proper, which is still to a large extent very much within classical statistics. All right. Something which I did not say at the beginning, I like to keep this as informal as possible. So if anybody wants to interrupt me or make a comment or have a question, and let them do it whenever he feels like it, and not wait until the 10-minute break or until the end, until Friday or something like that. Anytime. Yes?
Can you make the projection a little bit larger?
That's a good question. Is this the way to do that?
Yeah.
Will it remain? Well, that's one way to find out. I think it could be a bit sharper now. This one? Yes, yes, yes. Okay. Well, these are three sets of principles that not define but describe the area of data analysis. And since we're talking about principles, Gifi also has his principles, and I will briefly state his principles now. The first principle in Gifi, of course, it's again much more extensively treated in the book itself. There is no clear-cut distinction between exploratory and confirmatory. These are two very popular words these days, and many authors write as if there are two separate activities in data analysis or in statistics. I'm also using these two words sort of interchangeably. Two separate activities. One is called exploratory, and there everything goes. There are no rules. You can do whatever you please. There's also confirmatory, and in that area there are very strict rules. You must think of the model before you collect your data. It is not allowed to change the model during the analysis. Many rules like that. Very strict rules. Now these two words here, exploratory and confirmatory, are just two modern and somewhat specialized variations on a number of other words which I've written down here. Some of them may look familiar. There's deductivism versus inductivism, rationalism versus empiricism, optimism versus pessimism, inference versus data analysis, model versus technique, confirmation versus exploration. That's cheating, that's the same thing again. And Popper versus Feyerabend. Now, of course, I'm not going into any deep discussion of all these concepts over here, because that's Western philosophy for the last 2,000 years. And it would certainly take us too far to go in that. But the distinction here has many things in common with the distinctions I mention over here. And of course, people have been talking about these distinctions for ages and haven't gotten much further. So it's very safe for us to say that there's no clear-cut distinction between exploratory and confirmatory. Another thing is every data analysis situation has exploratory and confirmatory aspects. Another way to formulate the same problem, the same principle. Or it is impossible to abide by the rules of confirmatory data analysis. That would be another way of formulating the same principle. Another rule, of course, or another way of formulating the principle is that not everything is allowed in exploratory data analysis. There is no clear-cut distinction. The two things complement each other and should be used next to each other. There's another principle here which suffers severely from the fact that my black is sort of fading. In most of the situations we are familiar with, the standard statistical prejudice. The standard statistical prejudice is a term which is not due to me but to Kalman, the filtering person, does not make sense. The standard statistical prejudice is the fact that the data are a random sample from some population. And by a random sample we usually mean that they are independent and identically distributed. Now, for many of the data structures that I shall show you in this week, it is obvious nonsense, if you think about it, to suppose that they were generated by some sort of simple random process. Now, statisticians have found something to remedy the fact that this is obviously absurd, and they have invented superpopulation models. I don't know if you're familiar with those. They're sort of one solution, but it's a strictly, let's say, a sophistic or a verbal solution to the problem that for many data sets it does not make much sense to assume that they're independent and identically distributed drawings from some sort of population. This is not true for all data sets, obviously. There are many situations, if for instance in quality control or even in the data collected by bureaus of national statistics, in which the assumption does make sense. But for many data sets in the sciences, this cannot be defended very well, we think, Gifi thinks. The third principle is that we must explore the many-to-many relationship between models and techniques. Now the fact that I call this a many-to-many relationship is significant. In classical statistics, the relation between model and technique is usually portrayed as a one-to-one relationship. You start with some sort of model, and the properties of the model dictate the optimal technique, the type of technique you should use. Now this is obviously a one-to-one relationship because every model dictates its own technique. The reverse one-to-one relationship is also possible. You could also start with a technique and find the model for which that technique is optimal. That is uncommon, but possible. It's still the same one-to-one relationship. Now, Gifi thinks that the relationship between models and techniques should be a many-to-many relationship. In other words, that you should apply many different techniques to the same model, and you should apply the same technique to many different models. We shall see examples of that further on.
Excuse me.
Yes.
Does this suggest then that you shouldn't seek more general models where a particular data may require a special case of that general model? Because you seem to be suggesting diversity rather than trying to generalize.
I don't see how that would imply. You're saying that it implies that you do not seek more general models?
I'm asking if that's part of your principle. Because you're saying many techniques rather than search for a more general technique.
Well, this many techniques could include either very specific techniques or very general techniques. It's not necessarily true that the many diverse techniques that you would apply to any particular data set would all be very specific and focused on particular aspects of that technique. They could be sort of global, or they could pay attention to specific details. So it's certainly, I don't see that it implies that you should not develop more general techniques. Yes? If you have principles, yes?
Could you clarify your distinction between technique and model?
Well, basically, a technique is a function which takes data to representation, to output, to, well, whatever it is that a technique uses for representation purposes. Could be a graph, could be a table, it could be a technique is a function which processes data. And a model is a statement which says that some particular state of affairs is true. It could be an algebraic model which says that certain algebraic relationships are satisfied in your data. It could be a probabilistic model which says that certain stochastic relationships are satisfied. So a technique is a function which makes a picture in the general sense of making pictures. Could be a table, but makes a picture of data. And a model is a statement which says that a certain state of affairs is true. I'll go into that in more detail when I'm discussing the tools. If you have principles, you also must provide tools. The first tool that is discussed in Gifi is gauging. Now this is perhaps not a very optimal use of the word gauging. You'll have to judge that. I'm not a native speaker. I know we have sort of looked up the word in a dictionary, so perhaps a better word could be found. What gauging is outlined in blue below. A data set with known properties is a gauge. We want to find out how a particular technique represents these known properties. Now this activity is called gauging. What do you mean by a data set with known properties? Well, there are various examples of gauges in green down here. Probabilistic gauges. One probabilistic gauge that has been used a great deal, especially in multivariate analysis, is the multinormal distribution. We know, if we know that the data are a multinormal distribution, then we know very much about these data. We know what the critical aspects are, the things that the technique should pay attention to. So in that sense, if we know that the data are a multinormal distribution, we have a data set with known properties. There are also statistical gauges. They are not the multinormal distributions themselves, let's say the multinormal populations, but they are samples from multinormal distributions. And a statistical gauge is hardly distinguishable from number C, which is called the Monte Carlo gauge. The difference between the two is intended. That's more explicitly in Gifi 2. I mean, if you write them down like this, they look almost the same. But statistical gauges work with formulas, and Monte Carlo gauges work with computation. That's the basic difference between the two. But the starting point is the same. You also start with samples from some sort of specified parent distribution. Then there are algebraic gauges. And these algebraic gauges are perhaps familiar to the people working in psychometrics, but also people working in engineering, I would say. In psychometrics, for instance, the simplex, the Goodman scale are familiar algebraic gauges. So these are data sets whose properties are defined in terms of algebraic relationships between the data. In engineering, for instance, you have linear dynamic systems, which are very famous algebraic gauges. And then there are empirical gauges. That's a bit problematic concept. These things are gauges exactly because you have constructed them. You know their properties because you have defined them. You have used these properties to construct the data. Empirical gauges sort of looks like a contradictio. But there are data sets in physics and in astronomy in which many, many properties are known, as it were, about these data. There's a fairly recent paper by Stigler in the Annals of Statistics in which he applies a number of robust estimators of location to what I would call empirical gauges. These are astronomical data. He uses location estimators to estimate sentinel tendency, and he finds that how well they perform in terms of the known properties of these data. I mean, we now know what the distance is between astronomical objects, and the empirical gauges he uses are old data sets in which it was not exactly known what these distances were. So the concept of empirical gauges also makes sense. We will meet one empirical gauge later on. That's the first important tool, gauging. Now the important thing is that this is the tool which you use to study this many-to-many relationship between models and techniques. The models are the gauges, data sets with known properties. You can apply any technique within certain limitations, of course. I mean, if you have a rectangular data matrix, you must not apply a technique which does not handle rectangular matrices, but you can use any reasonable technique on any of these gauges and see what the technique does to the well-known properties of the gauge. So what it does, for instance, to the covariances of the multivariate normal, what it does, for instance, to the known distance between these astronomical objects. This is one of the tools you can use to investigate this many-to-one relationship. And again, I do not want to give the impression that this is new in any sense of the word. I merely want to give the impression that this is a new word, gauging. for an activity which many data analysts have been involved in for many, many years, but often from a somewhat different starting point and with a somewhat different emphasis. The second tool was the analysis of stability. Now this is even more classical. The basic idea of stability is that, it's also again stated in blue with red frills, a small and or unimportant change in data, model or technique should lead to a small and unimportant change in results or representation. This is called stability. Now again, people in physics and engineering will immediately recognize this concept of stability. It plays a very important role there. People in statistics will probably also immediately recognize it, and that will become more clear when I've gone through this list in green up here. The list in green is a list of the many types of stabilities that you can study, many types of stability that you can study. The first one, A, is replication stability. Replication stability is a very basic requirement in science, and it says that if you do something which you think, or if you repeat an experiment or a survey, if you repeat a survey or an experiment, then and you do not change anything important, then the same thing should come out. Of course, this is if this would not be true, then we could all go home right now. This is the sort of minimum requirement for communicability of results and for the fact that things hopefully remain the same at least for some time and for some period of time and in some respects. This replication stability also, of course, applies to techniques. If you apply the same technique to the same set of data, then the same thing should come out. And if you apply it to a replication of your data, then a very similar thing should come out. There's also statistical stability. Statistical stability is closely related to replication stability, only you don't do the replications. That's the difference. Statistical stability is replication stability without replication. That's a paradox. There is no opportunity or no money or no whatever to do the actual replication. You devise a probabilistic model which tells you what would happen if you would replicate your experiment. And of course, although that seems very close to replication stability, there's a large number of problems are introduced by the phrase, the model tells you what would happen if you would replicate the experiment. This is statistical stability. There's also stability under data selection, which is related again to statistical stability. And this is again connected with these bootstraps and jackknives that I mentioned earlier. Data selection is given a particular data set, take a subset of your data and perform the analysis on that subset. Then take another subset and perform the analysis on the other subset. Now if you take your subsets in a systematic way, and if you do not incorporate any new information in your subset selection mechanism, so if you take your subsets randomly or balanced, then the results of the subset analysis should be similar to each other and also to the results of the original analysis. Now this is the basic principle that the bootstrap and the jackknife that we shall meet later on are based on. It's data selection stability And data selection is now meant in terms of selection from one given data set. In statistical stability, it is meant in terms of selection from one infinite unknown population. That, of course, is again a very important distinction. Stability under model selection is another important type of stability that you often want. It's sort of familiar from regression analysis, for instance, under the label of multicollinearity. It's perhaps also familiar from the analysis of what is often called causal models. That's a horrible misnomer, but many people use it, so I will use it too. If you make a small change in the model and then fit your model by some fitting procedure, small and unimportant change, then the results should not change dramatically. So if you have, for instance, a regression model with a small regression coefficient and you leave out the corresponding variable, then you should not have a dramatic change in your regression coefficients. And this type of stability, of course, is also very important to have around, especially if you do not know what the correct model is, or if you only have a range of models that you can investigate and you're not sure which one it is from that particular range. Now that often happens in exploratory regression analysis and causal modeling. There's also numerical stability. Now numerical stability is very familiar, I would say. It's simply the fact that if you collect your data in 3 decimals and then do the analysis, you should not have very different results than when you collect your data in 4 decimals and then do the analysis. That's numerical stability in a nutshell. There's also analytical stability. Analytical stability studies the differentiability properties of your technique, and it's very important to analyze some forms of statistical stability. It could be that the map, the technique that you use to portray data, is a differentiable function. In that case, at least some form of stability is guaranteed, of course. Exactly the stability that is hidden in the definition of a differentiable function. So this analytical stability is something we shall also meet, especially in connection with statistical stability of our techniques. Then there's algebraic stability. Algebraic stability refers to algebraic properties of the data set, which can be used to study stability. For instance, many techniques that you use, regression, path analysis, many of these multivariate techniques are based on linear algebra, as Ben-Zakri's first principle so clearly explains. That means that the techniques that you apply are linear algebraic operations, and you can use that fact to study their stability. There are special stability techniques for linear operations. And then H, last form of stability that I shall mention. Again, there are many more words about this in Gifi. Stability under selection of technique. Now this means if you have a gauge, for instance, a multivariate normal distribution, and you apply 10 different techniques to that gauge, and 9 techniques show you the same thing, but the 10th technique shows you something completely different, then there's reason to look into the reason for why that occurs into more detail. Similar techniques applied to the same data set should not give widely different results. Of course, very different techniques which want completely different things applied to the same data set can give widely different results. If you compute the mean and the variance, it's not very strange that 2 completely different numbers will come out. But if you compute the mean and the median and the mode and the central tendency measures, and 9 of them are exactly the same and the 10th is different, then there's reason to be worried. Both tools, both the gauging and the stability analysis, are technique oriented. Now this means that our emphasis is on the technique and not on the model. This is a distinction with classical statistics, or at least with some generation of classical statisticians. I'm not exactly sure when it started, but there has been a phase in which statistics has been very model-oriented. These tools are technique-oriented, which means that they take the technique as a starting point. But otherwise, all of classical statistics fits in painlessly. This means that the usual operations of classical statistics, estimation is a technique, of course. It maps data into representation, parameter estimates. The sampling distribution and the standard error are measures of stability. It's clear. They're either statistical stability or they're analytical stability in the large sample case. Testing is a method of stability analysis. It tells you how large the probability is that something is found by chance. So it's really not a revolutionary new thing that I'm proposing here. It's merely a question of emphasis. And gauging is used, I already mentioned that. Gauging is used to study the correspondence between models and techniques, the multiple many-to-many correspondence. These were the, let's say, the remarks I wanted to make about, let's say, the general principles of data analysis, or the distinction, if such a distinction exists between data analysis and statistics, or about the principles used in the book by Gifi. This is the start of the second chapter, so it would be a sort of logical to have a 10-minute break now. But yeah, okay. Any questions? We can rapidly before the break. No? Yes?
Your algebraic gauge, an index number be an example of an algebraic gauge, consumer price index.
Well, the idea of a gauge is that you know very much about it already. You have lots of prior knowledge about that gauge. So I wouldn't be too sure whether that would apply to index numbers or to any. I mean, if it's a very well-known set of data of which properties are known, then perhaps yes. But in general, I wouldn't know. I must say I'm not too familiar with index numbers. I don't know how they look in general. So yes.
Is it fair to say that the techniques have more to say about models than vice versa?
Well, I would certainly hope so. It's largely a question of prior knowledge, of course. If there are many things you know about your data already before you start, then you can ask very specific questions. Very specific questions lead to a very specific technique. And a very specific technique gives you a very precise answer to the question that you have posed. But if you have very little prior knowledge about your data, which is a situation I'm more familiar with, then let's say assuming a model in itself is sort of tempting the gods. You're incorporating more prior knowledge than you actually have, which means that you're restricting the number of possible answers that you can get. And that is something which you do not want to do in many cases. So it's Tukey has a saying somewhere that it's much better to get an approximate answer to the right question than a very precise answer to the wrong question. And that is more or less what the distinction is. Yes?
I suggest another variety of stability.
Ah.
Stability under rearrangement of the data. If you're computing a mean, the result shouldn't depend on the order in which you sum the values, but in some cases, using a computer, it might.
Yes, certainly, especially for the variance, that is the case, yes. Yes.
There's some methods of multidimensional scaling and cluster analysis, the order.
I could very well imagine that, yes. Well, you certainly, that could, of course, be, I'm ahead. It's closely related to numerical stability, of course, because the reason why that happens is of the numerical instability of the algorithm.
In the case of the mean, it is, but take a clustering algorithm which you have to initialize by selection of seed points.
Yes, that's true. In that case, it's sort of a, let's say, local minimum type of problem. Yes. Well, that's a good suggestion. I'll fit it into my list, with acknowledgements, of course. Any more questions? Well, let's have the break then. 10 after, yeah.